All right, we'll kind of get started just reading the thing. If you guys printed off the notes, that was probably a good idea. This is like my favorite thing that we do this year in 10 math, this idea of proof by induction. And the reason why I like it so much is I know a lot of you guys had a really wonderful experience in geometry doing geometric proofs, and you all love them so much. And it really broadened your mind at how amazing proving things mathematically could be. And I wanted to be able to extend that to algebraic proofs. And these are like 100 times better than geometric. Geometric proofs are garbage. You have to like know things and remember them. Whereas algebraic, it's a series of steps that you take that are just a little bit better and more exciting. So let's talk about it. So this is called proof by induction, and it's really nice and straightforward and not necessarily simple. It can get really complicated, and it's sometimes a really hard concept to wrap your brain around, but it's still really cool. So if you guys have questions, you need to stop me. So like you can have free reign to unmute yourselves and stop me from going on if you have questions. Like please do, um, because I want you to ask questions. It's the whole reason we're doing this live as opposed to me just making a video, okay? So here's the principle of mathematical induction. All right, so it says, suppose we have some statement P of n, and we want to demonstrate that P of n is true for all n. So let's say we have a series, and we have a rule for the series, and we want to say that the sum is this kind of expression. So like what we've been doing with arithmetic and geometric series, finding that equation that we use to find the sum was really nice. But how do we prove that that's always true? And we use mathematical induction to do that. So even if we can provide proofs for the first term, the second term, the kth term, where k is some large number, we have not shown that P of n is true for all n values. So you can't just say, well, it's true for 1, it's true for 2, it's true for 3, and it's also true for this n value in general. You have to go a step further in mathematics in order to make it truly true. So this is why we use proof by induction. So induction is a defining difference between discrete and continuous mathematics. So discrete means that it stops, it ends. So you get to n and it stops. Continuous means that it goes on forever. So it's infinite. And this is really cool. Okay, so principle of induction. All right, we got a lot of stuff here. So in order to show that for all n, P of n holds, it suffices to establish the following two properties. So you show the base case, show that P of 1 is true. Okay, so plug in 1 for n, show that it's true. Then you do this thing, it's called the induction step, where you assume that the P of n is true and show that if P of n is true, then P of n plus 1 is also true. In the induction step, the assumption that P of n holds is called the inductive hypothesis. Okay, so you're making an assumption here, assuming that the thing you want to show is true, and then showing that it's true for the thing after k or the thing after n, and show that that's true as well, and then it kind of chain reactions. So having proven the base case in the inductive step, then the structure of n is such that any value can be obtained by performing the inductive step repeatedly. Okay, if you show that n is true, and you show that n plus 1 is true, by that chain there, you also know that n plus 2 is true, and n plus 3 is true, because you can show n plus 1 implies n plus 2, and so on and so forth. So think of it this way. So it may be helpful to think of the domino effect. So consider a line of dominoes, each standing on end and extending infinitely to the right. In class, I literally would have had dominoes and set them up and knocked them over so you guys could see this. But it's a really nice thing, okay? So suppose that if you knock over the first domino, okay, so the first domino falls over, and then the next domino falls over, and then the next domino falls over, and so on and so forth. They're all going to be falling over. over and over again. That's your assumption. Your assumption is that if one of them falls over, the next one falls over. With these assumptions, one can include, using mathematical induction, that all the dominoes will fall right. So if you see here, it says the statements are lined up like dominoes. So this is the first sum, this is the second sum, this is the third sum. Okay, if we knock over the first sum, so if we show S sub 1 is true, then it's going to fall over. So that's the domino falling over, assuming it's true and showing it's true. And then we go all the way to the end here and assume that the kth domino does in fact fall over. And then we want to show that if the kth domino falls over, that implies that the k plus 1 domino will also fall over. Okay, and if we can show that, that relationship makes it true always. It's a really cool, kind of tricky thing. Okay, so let's go through an actual example with this. So I provided an example that I wrote out with the steps, and we can kind of look at this first. So it says prove that this expression here, 1 plus 2 plus 3 plus, 1 plus 3 plus 5 plus 7 plus whatever, all the way up to the nth term, 2n minus 1, is equal to n squared. We want to show that this is true in general. So the steps of mathematical induction are to first verify that the first case is true. So plug in n equals 1. All right, if I plug in n equals 1 to this, so this is equal to this when you do the sum. So plug in 1, well, you get 1 equals 1. Okay, so if it's 1 equals 1, that means that that first thing is true. This rule here works for S sub 1. So S sub 1 is true. Then assume that the formula is valid for n equals k. So assume that the kth term is true, that the formula is true. So if I plug in k for n, I get this expression here, okay? So this is me assuming it's true. I'm taking this thing here as given. So if you guys remember the given pieces of proof, this is what our given would be. We're assuming it, so it's given for us. Then what we do is we use this expression here. So we use this one to show that the k plus 1 term is true. So what we're trying to do is, if you plug k plus 1 into this thing up here, so you get k plus 1 squared for n, we're trying to show that the n equals k plus 1 is a true approximation of this, okay? So the way you go through and do this is you always start with the given and write it down. And then you look at one side of the given and you say, okay, well, how could I change this into something else? How could I change it to be the k plus 1 term? Well, just add on the next number in the series. So if this was the first part of the series, the next number in the series is this expression here, because the next one is always 2n minus 1. So it would be 2 times k plus 1, because it's the k plus 1 term, minus 1. That would be your next term. So you add it to one side here, but then you also add it to the other side in order to keep the math correct. Okay, so you add it to both sides, because that's the k plus 1 term. It's the k plus 1 term. Okay, and then if we take this expression here and simplify it, well, this is 2. So we simplify it like this, put it together like this, and then you notice that can factor, and it becomes this expression here. We've shown that the k plus 1 term, when you add it on to the thing that we assumed was true, the n equals k term, we get the expression that we would expect to get. And that's sufficient enough to prove. That's proof by induction, okay? So it's a little bit tricky. It's a little bit wacky. And we'll go through and look at it a couple of different ways. This is really laid out using logical mathematics that we're used to, but we can do some other things to make it work as well. So since the formula for the sum n equals k produces the same result as the direct computation of the sum, so because when we added this thing to both sides and did the manipulation, we got this, which is the same thing as if we had plugged k plus 1 in for n up here, then it's the same thing. Okay, that means it's true. That means proof by induction worked, and that means we've proved it for every single value of n, past, present, and in the future. So we can go through and do this with multiple different types of series. And it can get really, really complicated or really, really easy. So what I like to do for each of these kind of expressions is to write down each step. So your first step is always to show the first term is true. So n equals 1 is true. So you say show n equals 1 is true. Right? That's the first step. To do that, evaluate s sub 1. Okay, so s sub 1 is equal to 3 times 1 minus 2. And this is just 1. And then what we want to do is we want to see, well, did this rule work for n equals 1? Well, let's plug it in. 1 times 3 times 1 minus 1. Nope, did not need that one. Divided by 2. Okay, well, what's this going to be? Well, 1 times 3 times 1, so this is 3 minus 1, which is 2, so 2 over 2. Well, that's just 1, 2. Okay, so because s sub 1 is 1, and because the thing that we're trying to use also works when you just plug in 1 for n, the n equals 1 term is true. Student green. Okay, so that's the first part. All right, after you got the first part, you want to write down what you're assuming is true. Well, we're going to assume that this expression right here is true. So we're going to assume that 1 plus 4 plus 7 plus dot 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 plus 3n minus 2, we're going to assume that this is in fact equal to n times 3n minus 1. Okay, so this is what you're assuming is true. So we're assuming that's true, and we're going to use this in the future, except let's change these to k's because it starts to get confusing if you don't. Let's erase them. So assume n equals k is true. All right. So now we're going to use this assumption and show that it is true for the next part. Okay, so let's write down our series again. So it's going to be 1 plus 4 plus 7 plus dot 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 plus 3n minus 2. Okay, so if this is my series for n equals just n itself, well, if I plugged in k, it'd look like this. Okay, so that's my kth term being plugged in. Well, what would me adding on the k plus 1 term look like? Well, it would just be plus 3 times k plus 1 minus 2. So this term here is my n equals k plus 1 term, and this term here is my n equals k term. Okay, so these two things here are what separate the difference between the n equals k plus 1. Okay, this expression now is my expression for the n equals k plus 1 term. All right, this would be the sum. This would be s sub k plus 1. All right, and we want to show that this thing here is equal to my expression up here with k plus 1 plugged in for n. I just want to see, well, what if I had just plugged in k plus 1 into my thing that I think is true? Well, that would be k plus 1. That's terrible. Can't even see it. All right, let's do it right. K plus 1 times 3k plus 1 minus 1 all over 2. We want to show that this thing here is this thing here. Okay, and if we can show that, then it's all good. Now the question is, how do you do that? Well, we use our given. Okay, well, what did we assume was true up here? We assumed this was true. All right, we assumed that this thing right here is equal to this thing right here. Conveniently, this right here is just this side, okay? So it's just this side right there. So I can go through and say, well, I assume that this becomes this, right? You can't see it because I wrote too much. This becomes this, right? So I can replace this expression here with this thing, all right? So let's plug it in. So I end up with k times 3k minus 1 plus my expression right here. This is 3 times k plus 1 minus 2. Okay, I forgot the over 2 over here. Okay, so now that I have this expression right here, my job is to manipulate the left side to look like the right side. And that's all that I have to do. Well, let's do that. So to manipulate this, let's distribute everything. So 3 times k, 3 times 1, so 3k plus 3 minus 2, so it's 3k plus 1 right here. And then distribute this as well. This becomes 3k squared minus k, so this is 3k squared minus k over 2 plus 3k plus 1 divided by nothing, because we can't do anything yet. But if I wanted to make this over 2, I could multiply it by 1 in the form of 2 over 2, and then I could put everything together. So this would become 3k squared minus k plus 6k plus 2 all over 2. And then I go a little bit further and I say, well, this expression here is just 3k squared plus 5k plus 2 over 2. And then can I factor this expression here? Well, yes, I can. I can factor that. This becomes 3k plus 2, and then k plus 1 over 2. And then, if you guys have been paying attention, you should notice that this expression here is very similar to this expression here. All I need to do is see, well, 3 times k is 3k plus 3 minus 1 is plus 2. Okay, so then these two things are equal. So that is proof by induction right there. It's beautiful, isn't it? Aren't you guys glad that I'm trying to do this virtually?
Sorry, so after you plug in the 1 for the 3n minus 2,
Mm-hmm.
then what? I kind of got lost after that.
Right here.
Yeah.
So then I go through and do the proof by induction. So let's look at another example. And I'm going to be honest with you guys. You all have A's, unless for some reason you have a B. We're just doing this because I really like this and I think it's cool. So I appreciate you guys trying. There's no actual necessity for you to know it. I'm giving out so many A's this semester, it's not even going to be funny because I made everything you just do it. So don't worry so much if it's confusing. I just want you guys to try it. We'll have office hours tomorrow and I'll go through all the practice problems during office hours like I did last time if you guys wanted to join that and wanted to see how it's done. Okay? So let's look at the next example. So in example 3, it gives us a sum and then asks us to go through and show that it's actually true. So this is a prove thing again. Okay, so you use proof by induction. It's always the same thing over and over and over again. Okay? So you start off with the n equals 1. So show n equals 1 is true. Okay, to do that, you want to see if the left side and the right side is true. So you do 1 over 1 times 1 plus 1. So that's my first term, is equal to 1 over 1 plus 1. Well, it's just 1/2 equals 1/2. So that first case is true. Our first domino is going to fall. All right, so now we're going to go through and assume that the kth domino is going to fall. So we go, well, let n equal k be true. So assume that the kth domino falls. All right, so what does that imply? Well, that implies that this expression here is true for k. So 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus dot 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 plus 1 over k times k plus 1 is equal to k over k plus 1. All right, so we're assuming that this is true. All right, now what we do is we go through and say, well, if that's true, all right, if that's true, what happens if to this sequence here, all right, so to this sequence, we add on the k plus 1 term? Well, what is the k plus 1 term? K plus 1 term is, well, we just plug in k plus 1 for n here. So it's 1 over k plus 1 times k plus 1 plus 1, which is equal to 1 over k plus 1 times k plus 2. Okay, so this is the k plus 1 term right here. All right, that's the final term afterwards. Okay, the final term after the kth term. Now, all I have to do is I have to go, well, what would happen? Well, if I add this term to this side here, it's the same as adding to this side over here. So I just add it to both sides. And on this side, I end up with a single expression. And on this side, I end up with a single expression. It's this, k over k plus 1 plus 1 over k plus 1 times k plus 2. Okay, this is the sum of my series for the kth term. And this is my k plus 1 term being added onto it. And I want to show that this is equal to this expression here with k plus 1 plugged in. I want to show that if I would have just plugged in whatever my k plus 1 value is, it would be true. Those are terrible parentheses, but you guys get the idea. Okay, I just want to show that this expression here is true. Let's modify this a little bit to make it less confusing. Okay, so I want to show that this thing is equal to this thing. And if you can show that by induction, you've proved it. Okay, so to manipulate this, I notice there's a k plus 1 here, a k plus 1 here. Let's get like denominators. So I'm going to multiply by k plus 2 over k plus 2. So I end up with k times k plus 2 over k plus 1 times k plus 2 plus 1 over k plus 1 times k plus 2. And if you guys notice, the reason why I like this so much is because you have to use literally everything you've done before in order to get the correct answer. So it's a nice way to sum up the year, I think. All right, so this expression here, if I go through and equate it, remember my goal is to show that this is equal to k plus 1 over k plus 2. Well, to do that, I can just simplify the top. I get k squared plus 2k as this expression right here, put them together. So put my fractions together, I get plus 1 over k plus 1 times k plus 2, like so. And again, I'm trying to show that this is equal to k plus 1 over k plus 2. Okay, so this expression on the top here can factor, and if you guys remember, it factors to k plus 1 quantity squared. So this becomes k plus 1 quantity squared over k plus 1 times k plus 2. And this is equal to k plus 1 over k plus 2. Is it equal to it? Well, cross these out, and it is. It is in fact the same. So there we go. That's proof by induction. Okay, you've shown that the first domino knocks over. You've assumed that if you knocked over a domino in the middle, and by assuming that you knocked over some k domino in the middle, so it could have been the third domino, it could have been the fourth domino, it could have been the fifth domino, you're assuming that that implies the next domino is also going to fall over, and this proof shows that it does, because when you add that next thing on, it simplifies into it. And it's a really nice way to prove things. Okay, do you guys have questions?
Where did you get k plus 2?
On the bottom here,
Yeah.
from up here. I said that k plus 1, when I plug in the k plus 1 term over here, is just k plus 2. I simplified it.
Wait, so how come it's k plus 1 plus 1?
Because when I find this term here, okay, this thing is what I would get if I had plugged in k plus 1 to n over n plus 1, and then you let n equal k plus 1, and you plug this expression in for n, so you end up with k plus 1 over k plus 1 plus 1, or this thing here.
Okay, yeah.
Okay? So there's one more type of proof that we can do for this, and I'm trying to keep this just to 30 minutes. Okay? It's a riot. And that's proving things are divisible by stuff. So I kept it to series in the first two because that's what we've been working with, but you can use this to prove a lot of different things. Okay, so we want to prove that n equals, or n squared plus n is divisible by 2. Okay, so let's go through and do that. It's the same steps. It's no different than it was before. It's the same steps. You go through and you say, well, let's show that one case is true. Let's show that the first domino falls over. So show n equals 1 is true. Well, plug in 1 for n. 1 squared plus 1 is equal to 2. Is 2 divisible by 2? Yeah, so 2 is divisible by 2. Okay, good. Our n equals 1 case is shown. All right, we know that that's true. So we know that we knocked the first domino over. Well, let's pick some random domino in the middle of my chain of infinite dominoes. So the kth domino. So it could be the 100th domino, it could be the 1000th domino, it could be whatever domino you want. Let's assume that that one gets knocked over. But the question is, how do you express that mathematically? So let's assume that n equals k is true. Okay, assume n equals k is true. Well, that means that k squared plus k must be equal to some integer, I'm going to call it I, times 2. It must be equal to an integer with a factor of 2 in it. So 2 times some other integer is going to be equal to this expression here, because we're assuming that when you plug in the value of k, it's going to be divisible by 2. So if this is equal to this expression here is divisible by 2. And then just say I equals some integer. Okay. So now what we want to do is we want to show with our assumption that the k plus 1 term expression thing is also true. Okay, so this gives us, we have to break it down. Okay, so the first step is show, well, not first step, but n equals k plus 1. All right, so show that. So let's let n equal k plus 1. And plug it into our expression up here, n squared plus n. So end up with k plus 1 squared plus k plus 1. All right, now what we want to do is we want to show that this is divisible by 2. And it looks very tricky. It looks like we won't be able to do it, but you can go through and see what happens. So let's expand this a little bit. So this becomes k squared plus 2k plus 1 plus k plus 1. And then you have to be really, really careful, okay? You have to remember, what did we assume was true? Okay, our given is up here. This is given in this proof down here. So is there a way that I could find this expression here and do a substitution in this thing down here? Do I see a k squared plus k? Why, yes, I do. It's right here. this is k squared, and this is k. And conveniently in math, we can reorder things, right? So I can rewrite this as k squared plus k, that's a 4. It's close to a k though, because k could be anything. Plus k plus 2k, and then I'm going to put these two ones here together. This is plus 2. Okay, and then by my initial assumption that the kth term is falling over, so if this one falls over, that means I have 2i right here. So this becomes 2i. So you're going to sub in assumption. Right here. That's equal to 2i. So you sub in that assumption. So I get 2i plus 2k plus 2. Is this divisible by 2, this expression right here? Yes, it is, because I can factor out a 2. I can factor a 2 out of every term, so this becomes 2 times I plus k plus 1. Okay? And this is divisible by 2. So because we've now shown the first case is true, shown that we assume the kth case was true, and if we assume a domino in the middle gets knocked over, knocking over that middle domino also knocks over the next domino. We can then use that and extrapolate it out. Okay, well, if assuming some domino in the middle got knocked over, and it implies the next domino got knocked over, well, why can't that next domino be our k domino, and then it becomes a +1 and +2 and so on and so forth. You can keep knocking them over using that mathematical logic. So that's proof by induction. I think it's pretty cool. It's a lot of
Mr.
fun.
Babcock,
Yeah,
you like Domino's or Giorgio's better?
Domino's.
I quit your class.
I'm actually from Buffalo, New York, so all the pizza here is crap. I'm gonna be honest. I make my own pizza actually, rather than going and buying pizza. Like I raise the dough from a small little yeast, and it turns
That's
into all
pretty cool.
bubbly and
I've always
delicious.
wanted to try that.
Handmade pizza slaps. It's the best.
Yeah, it's pretty good. It's really easy too if you have a bunch of yeast and flour. Okay, so that's the moral of the story. I know this is really tricky. Okay, this would be like a week in class. We'd be going over this in a week in class doing practice. I would have done this thing that I just did in one day, and then the next day we would have gone over the 2 homework problems I gave you, and then done some sort of sharing circle the rest of the time. And then the next day we would have gone through and done practice problems in class with some homework, and then we would have reviewed, and then you would have had a quiz. This would have been a whole week for just this one idea. So my plans for next week. All right, I'm obviously going to give you guys a final assessment, but everyone has an A unless you don't have an A. I'm sorry if you don't. There's like 8 people who don't. Okay, but you could still get one by turning in the work that you're missing. Like it's still possible. Okay, everyone has an A unless you don't. But I want you guys to try the 4 problems I'm going to assign on Monday. Okay, so I'm going to assign 4 problems as a summative assessment for our sequence and series. Those of you who were all like, oh, IB is going to be amazing. I need to go do IBSL/IBHL. If you were one of those people, 3 of the 4 problems will be IB sequence and series problems that they would have put on the SL test. Okay, so I want you guys to see them and try them so you can get a feel for what would those ideas be. Well, sequence and series is fresh in your mind, and then it's real low stakes. I'm not going to grade this real crazily, you guys. I just want to see what you guys can do. Okay, try your best. If you're like, I don't have any time to do that because I need to walk my dog or something like that, that's cool too. I just want you guys to try it. As long as you do it, you'll get all the points. If you don't do it, I'm obviously going to fail you, but it'll be fine. Okay, so do you guys have any questions on this? I'm sarcastic about the failing thing. Everyone has A's.